Okay, and our fifth and final equation comes from our one displacement formula. It looks like this. So what I'm going to do is I'm going to find our fifth and final equation. So what we're going to do is we're going to get rid of time, because if you look at the five formulas, or when you have a chance to look at the five formulas at the end, you're going to find that each of those formulas has maximum 4 variables in it, and there's really the 5 that exist. So you always want to eliminate one of them so that you can solve for a particular unknown. So I'm going to take this equation. What we're going to do is we're going to get rid of time. So I'm going to isolate for time here. So V2 minus V1 over A is going to equal delta T. So knowing that, I'm going to do my substitution over here, which means I'm going to have V2 minus V1 over A. That's all squared. So cleaning this up a bit, delta D will equal V1. Oops, and I also have to do that delta T substitution as well. So delta D equals V1, and we will have V2 minus V1 over A. So delta D will equal, I'm going to common factor out. Let's try that. Do it different every year. So I'm going to try common factoring out a V2 minus a V1A because it's common in both terms. You see here and here. So if I do that, what am I left with? I've got a V1 plus 1/2 A, and then I still have one V2 minus a V1 over A, and it's no longer squared. So trying to clean that up a bit. So I'll have a V2 minus a V1 over A. And inside, the A's cancel, which is kind of nice. And I'm left with a V1 plus 1/2 V2 minus 1/2 V1. So that will simplify down for me. V2 minus V1 here. Oops, lost my equal sign. Now the board's not working with me here. V2 minus V1 over A. And inside, that's going to simplify down to, similar to what it did before, 1/2 V1 plus V2. Oops, 1/2. So that being said, with that simplification, I'm going to factor 1/2 out of that second bracket, and I'm going to get rid of the A as well. So I'm going to have 1/2 A. So I factor those out of those terms, and I'm left with V2 minus V1 and V1 plus V2. And for those that remember their grade 10 math and haven't totally erased those wonderful memories, that's a difference of squares. So delta D will equal 1/2 A. And in brackets, I'm going to have V2 squared minus V1 squared. Now, I want to avoid fractions. So that A is in the denominator. I kind of misrepresented that. I apologize for that. So I'm going to multiply both sides by 2A. All right, just to get rid of the fraction. So I end up with 2AD equals V2 squared minus V1 squared. And the formula that we're going to use is V2 squared equals V1 squared plus 2AD delta. Okay. There's our fifth and final formula, kinematics formula, that we're going to have to be able to use. All right. So there are the 5 formulas. And you have a summary sheet right here of the 5 formulas. Please be accurate here. Okay. This formula right here, okay, is for non-uniform motion, or sorry, for uniform motion, when there's no acceleration. Uniform, can't spell it. So uniform motion, and that is when acceleration is equal to 0. I'm really having trouble at this point. equals 0 meters per second squared. Okay, that or should not be there. Get rid of that. And then these are your equations, okay? Your 5 kinematics equations when acceleration is not equal to 0 meters per second squared. That would be non-uniform motion. All right, so how does this work? Well, I've given you 6 equations in total, but 5 dealing with non-uniform motion. And what it is, it becomes a decoding process. So you're writing down information, you're decoding what you need and what you don't need. So the first example, James, a dragster, reached a speed of 628 kilometers an hour from rest, in 3.72 seconds. How far did he travel in that time? So what information is given? And this is where that decoding process comes in. He reached a speed of 628. So that means if he reached it, that was his final speed. That's his V2. Now here's something that I start off immediately with. We are working in SI standard, so we need to work in meters per second. So we do need to convert that 628, and you need to divide that by 3.6, if you recall. So that's 174.4 meters per second. And I'm going to put right, because that's the direction I'm going to have the dragster going. Now we're given a time, so we know delta t is 3.72 seconds. And we want to know the displacement. How far did he travel in that time? In order to solve these questions, you need to have 3 pieces of information. So there is one piece of information that's given, it's just not in a numeric format. And for some of you, hopefully you've noticed it, it's this one right here. From rest. From rest means that they started at V1 equals 0 meters per second. Now I have 4 pieces of information. I have V1, V2, delta t. I'm looking for D. And as I said before, it's like decoding. You now know the 4 pieces you have. You're looking for a 5th. So what do we want to find? You need to find that correct formula. In this case, this one right here has a V1, a V2, and a time. So we're all set to go. So that means we'd be using delta D equals 1/2 delta t V1 plus V2. All right, so it's straight decoding. There's no mystery to it. The tough part, or the part that I'm going to be most interested in, is can you find that information? Because after, it's just a matter of figuring out what formula suits our situation here. So 0 plus the 174.4. When you calculate that out, you get 0.5 times 3.72 times 174.4. We get 324.4 meters. And that would be to the right. So therefore, traveled 324.4 meters to the right. Okay, next one. Consider a Ferrari moving at 20 kilometers an hour, accelerates to 230 kilometers an hour in 7.5 seconds. As it does this, it covers an unknown displacement. Find the displacement that was covered here. Same type of question. The only difference is, the point I'm trying to emphasize here, first of all, decode. So it's moving at 20 kilometers an hour. So that is your V1. All right, again, a lot of the questions you do have to convert. You need to work in meters per second. So 20 divided by the 3.6, so 5.6 meters per second forward. Then speeds up, accelerates to 230 kilometers an hour. So divide that by 3.6. So 230 kilometers an hour forward. And now it's doing 63.9 meters per second forward. Gives us a time again. And we know it's 7.5. Again, we're looking for displacement. So this particular example, just in the order here, we know that we're going to be using the same formula we just did because it's the same information that was provided. So just finish this question off. And the difference, again, first of all, I want to show that V1 and V2 can be given numerically, or they can be in the previous one not given numerically, you need to interpret the question. And in this one, it's so important to make sure you do convert your units. So 1/2 times 7.5, and in this case now, we need to add those values together to get our final displacement. So the 0.5 times 7.5 times that's the 63.9, and we get a total of 260.6 meters. So therefore, he traveled 260.6 meters forward. I have virtually the same question, just that V1 and V2 in a different form. So using the same Ferrari, same information, okay, calculate the acceleration. So we knew the V1 was 5.6 meters per second forward. We know V2 was 63.9 meters per second forward, and we knew the time was 7.5 seconds. Now we're looking for an acceleration. So again, it's a process of decoding. You go back to your 5 equations and you look for the information. So we know a V1, V2, and we know a time, and now we're looking for an acceleration. So you scan through them and you find that this one here has V2, V1, time, and acceleration. So we're all set. So V2 equals V1 plus A delta T. 63.9 equals 5.6 plus, we're looking for that acceleration at 7.5. So now it just becomes a process of solving for A. So subtracting 5.6. So we get the 63.9 minus 5.6. So we have 58.3 equals 7.5A. Divide both sides by 7.5. We get an acceleration of 7.8 meters per second squared, and it'll be forward. So therefore, the car accelerated at 7.8 meters per second squared forward. All right. So I have 2 final examples, and rather than cramming them in, I'll finish them up in a short third video.